Okay, great. Well, thanks. I think we're gonna take a little bit of a direction today to talking about a slightly different kind of model family called hidden Markov models. And there's a couple people I think in this class who are going to be using hidden Markov models for their projects. So I thought this is an example where we kind of move the syllabus around and move this up a little bit. I think we can certainly tweak these examples and include more detail later in the class if needed. But I think this is a good primer. Let's see what this is advancing. So kind of what we're largely going to do today is kind of talk about the motivating examples for what HMMs are. Without too much detail, kind of talk about a little bit about the background and the notation that we use when we talk about hidden Markov models, and then we'll start talking about some really real world examples of using hidden Markov models in practice. There's a ton of background out there. We were talking to Brielle right before class started about the great paper that Brett McClintock and co-authors published in 2020. That's a really good background for people who are unfamiliar with these models. There's a bunch of other references out there. The first are these books by Zucchini et al. That are really good references for using R. The books are, I think that both versions of the book are free, and so you can just download them from the internet. The other two in the middle here, the Jackson et al. And the DEPMIX S4 are both R packages that we'll talk about the latter of those today, but I think that both of those are really accessible. And then there's a lot of going back, sorry. Other kinds of examples that we'll talk about. So to date, we've talked about state-space models, and the way that we've talked about them has been, we've been focusing on thinking about time being discrete. So we have population counts that are measured at regular intervals in time. But the quantities of interest, those population sizes or counts, have been continuous variables, right? Because we often model those in log space. So in the notation of, say, an ARIMA model, we might model temperature or population abundance, and the x that's kind of being modeled is say the natural log of temperature or abundance. In the context of state-space models, they're state-space models because they consist of two different types of models. We call it a latent process model, which we don't directly observe, and so this is often, in this class, we describe this as kind of our x's. And we have a data or an observation model that sits on top of it, and that's the model that links our observations that are corrupted by sampling and measurement error to that underlying state. So our data y's are linked to our x's through that observation model, and we assume, for example, that both of these models might be normal in the case of MARSS models. This is kind of what they look like mathematically, and this is something that I think everybody's familiar with at this point. This model just has a random walk in say log space. We have population size is our X model, and then we have our observation model on top of it, and both our epsilons and the deltas are normally distributed. So in this case, like as I was saying, time here is discrete, but our data that we observe, our y's and our x's, are both continuous variables. Right. So we can make these models more complicated, and I think that Eli and Mark have talked about this. We can do things like include autoregressive coefficients or moving average processes, which might let these models be more flexible. But one of the limitations of these kinds of models in general is that they can't handle discrete shifts or kind of changes in regimes or states very well. And so there's been a lot of work on this in ecology, over the last decade or two, but people talk about tipping points. And when we think about tipping points, we have some ecosystem state or process up to some intervention. And then all of a sudden things get reorganized and we have a new state. And so I think that these transitions are really what the focus of these types of analyses are on. And there's a lot of other examples out there in both marine and terrestrial systems. So in addition to those kinds of thinking about regimes in the context of tipping points in ecosystems, there's a lot of other kinds of switching models that have also been studied. There's several examples in fisheries. Tessa Francis had a really good paper using some similar Mars models to think about regimes and thinking about how, in this case, a community of ichthyoplankton changes in cool and warm waters off of the Oregon-Washington coast. There's a lot of other applications of these kinds of switching models too in ecology. We have, I think probably when we think about other types of models with latent states, one of the most commonly used are these mark recapture models, right? Where mark recapture models also have discrete time, but they're different from what Mars models are doing in that the observations are binomial. They're whether an animal lived or died, or they're there may be things other than continuous variables. We might be also interested in thinking about regimes or changes in behavior, for example. And so I've done some work with some other some NOAA colleagues who have been putting suction cup tags on killer whales, and they're ultimately interested in kind of what's the change in behavior of whales, for example, when vessels approach. And so do whales take off, or do they change their foraging behavior? And that kind of discrete change is different from the kinds of models we've been doing so far. So these kinds of underlying or hidden state behavioral models are really popular in ecology. There's a few packages out there, including this. I think that Brett McClintock is also an author of this R package down below, which is useful for taking telemetry data. So these are kind of pairs of locations in time for tagged animals and looking at identifying patterns of, say, foraging or resting behaviors. So there are a lot of other kinds of approaches out there to thinking about regimes and detecting change points in data. These are approaches that we won't talk about for this class, but there's kind of there's algorithms like these stars tests, which are a series of sequential t-tests. You could do just kind of a brute force model selection approach, which is ugly, but you could just write a monster loop over all of your data points to look for the most likely data support for where a change in, say, a slope of this b parameter might exist in time. But that's not really what we're after here. So these are some data that I simulated. They're just from a kind of a regime model where we have two underlying states of the system, and you can kind of see in this case this might be say water flow or something. And when we take this data and plug it into Mars, we can actually get a really good fit to the data. So in this case, you might ask, why would we need something else? And in some applications, you don't need to fit this with other models. This is totally fine. But the challenge here is that when we fit these kinds of data sets when we use Mars to fit these kinds of data, one of the things we can't get out of it are thinking about our last slide. What's the probability of transitioning between, say, a high flow and a low flow regime, or how long is each of those regimes expected to last, or given our data that we've seen so far, what kind of regimes might we expect in the future? So there's a lot of applications of these kinds of models in other fields. This has been widely applied to patterns of speech and text recognition, bioinformatics, as I said, animal movement, environmental data, and finance. So in theory, so like we had before, with a Mars model, we had time as a discrete process. With a hidden Markov model, we also have time as a discrete process, and we're going to be transitioning between those time steps. But that transition is going to be discrete rather than continuous. So our state is not going to be a continuous variable anymore. It's going to be a Markov process because our state at time t, our x, is only dependent upon the previous state, our x at t minus 1. Our x doesn't depend at all on future values of the system. And so this is exactly, this should be totally familiar because this is exactly the same logic behind like the Markov process with the MARSS model. So we can write our entire history of x's as this vector below, which are all subscripted by time. Okay, so in thinking about the HMMs and a difference with MARSS models, one of the key differences are if folks have worked with, say, age-structured population dynamics data, you've estimated a transition matrix representing kind of how populations change through time with survival and fecundity rates, for example. With a hidden Markov model, we have to estimate a similar transition matrix, which I'm going to call gamma here. And so ultimately, for each of our states, we have to estimate the probability of transitioning from state I to state J, from going from being in state I at time t to state J at time t plus 1 is gamma, and that gamma is going to be subscripted ij. But when we think about each of these different combinations of states that we could be in now, and each of the different states that we could be in the future, we have to create this transition matrix gamma, which for this example, I've assumed that we have 3 potential states that we could be in, and 3 potential states that you could be in the future. So these could be like given that you got vanilla ice cream today, and you have 3 options between the vanilla, chocolate, and strawberry, what's the probability that you're going to get the same tomorrow, or the same a new flavor? And in this case, that's not maybe necessarily a Markov process, or maybe it is, depending on your preferences. So so this gamma matrix is going to be dimensioned based on how many states are in the system. That's something you decide a priori, rather than something that's decided by the model. Each of the elements of gamma here can be fixed a priori too, so they can be shared. So gamma 1, 2 can be the same as gamma 2, 1. They could be fixed to constants and not estimated. And then any of these elements could also be estimated to be 0. So it just really depends on the kind of question that you're interested in. I think in like a thinking about like a mark recapture type model, that's also can be thought of as a hidden Markov model. But you can think about the transition probability only kind of goes one direction, right? Because if you're alive, you can only die once, and then once you're dead, and you can't transition out of that state. So so these kinds of matrices need to be configured really for the specific application that you're working on. Okay, so to understand kind of how the data work, I think that it's useful to think about just how to simulate this. And this is, a super simple example, but I think that if you're going to be working with these models for this class or in the future, I think that just starting with just on the R code side of things is the best way to do this. And so in this case, what we need to do to simulate a kind of a trajectory is to initialize our initial state. And so in this case, I'm going to simulate an HMM with just 2 states, and it's going to be randomly assigned in the first time step. Then we also need to create a transition matrix, which I'm going to call gamma here. And the gamma is just going to be a 2x2 transition matrix where there's a 90% chance of being in state 1, given that you're in state 1. And so, and then, the other elements are the 0.1 is the probability of transitioning from 1 to 2. 0.2 is the probability of transitioning from state 2 to state 1. And then 0.8 is the probability of staying, transitioning, or basically remaining in state 2, given that you're already there. Then for every time step, we can just write, essentially write a loop where for every time step, we just create, basically sample a new vector of size 1, and the probability of being in state 1 or state 2 is just going to be dependent on which row of gamma we're going to be pulling from. So if we're in state 1, then we're just going to take the corresponding elements of gamma, which is in the first row. If we are in state 2, though, we're going to be doing the opposite. So this type of model, or this type of code here, is just going to create a sequence of x's that's just going to be 1 or 2 at each time step. with these specified transition probabilities. Okay, so this is kind of what the data would look like that you get out of it. In this case, the transitions are random. And so if we were to set the seed or run this for more time steps, we would get a different sequence out of this. But you can see that that once, this is not surprising given our initial gamma, but the persistence states or persistence probabilities are fairly high. They were 0.9 and 0.8. So once we're in state 2, the chances of staying there are going to be pretty high, or vice versa for state 1. Okay. So thinking more about what that gamma represented. So gamma can be seen as this matrix of one-step transitions. If you're interested in doing projections or thinking about longer horizons, you can certainly do some fancy math to calculate things like what's the stationary distribution of the chain. And so there's a lot of work on this in some of the references that I talked about, really beyond the scope of today's lecture and beyond the scope of the class, but just to know that there's a lot out there that can be done with those gammas. Okay, so there's two general types of ways that we can think about parameterizing gamma. So gamma can be homogeneous or stationary. And so in this case, gamma doesn't depend on time, it's fixed. Or gamma can be non-homogeneous. And so in this case, we could model the transition probabilities themselves as time varying or as some other function. For this class and these examples, we're only worrying about the homogeneous case. And so if you think about the loop that I wrote before to simulate our trajectory or our x's, gamma was initialized outside of the loop, and it wasn't changed as we iterated through each time step. We didn't pick a new gamma. We kept that constant for all time steps. Okay, so we've talked kind of about, so gamma is going to be constant, but then we can think about what effects covariates might have on either on the data or the states of nature. So covariates can affect the HMMs in one of two ways. They can either affect the means, and so these are kind of the mean states of the system, or they can affect our transition matrix, which is gamma. So the gamma, or including transition or covariates on gamma, is a little bit challenging because there's a couple of nasty constraints on gamma. One is that because these are probabilities, all of the elements obviously have to be between 0 and 1. And then second, there's these weird constraints. And so if we think about each row of gamma, it has to be normalized to sum to 1. And so so if you're in state 1, you can't just leave that vector has to sum to 1. So because of those weird constraints, there's a few approaches for including covariates. Multivariate logit regression is probably the most commonly used, and so I think we're not going to be worrying about that so much in this class, but that's one way to deal with it. And so I think what I was going to do is take the example that I showed before, and then I wanted to include a covariate that was kind of related to time, and let those transition probabilities change through time. And so in this case, if we just have two probabilities, we can use logistic regression, which is a lot easier than the multivariate logit regression. But we can let the covariates affect the transition between state 1 and state 2, which is gamma 1, 2, and then in blue, the opposite of that, which is the probability of going from state 2 to state 1. And so in logit space, I modeled each of these trends as linear, and we back transform to normal space. We get this a little bit of an exponential increase. So I think one of the things to think about is now that if I was to simulate our x's again with these time varying transition probabilities, what is the effect going to be in terms of our state? If we create our series of x's, what's going to change? And so here's kind of the code that I used to do that. You can see just as before, our gamma is initialized to be outside of our loop. in this case, we have each of our transition probabilities, which are the functions of time, are going to be updated as gamma 1, 2 and gamma 2, 1. Because we only have 2 probabilities for each of the rows of gamma, the persistence probabilities are just 1 minus the corresponding probabilities in that row, and then we can update our state as the last line in the loop. So that's kind of a brute force way of doing this. And then when we look at kind of what our sequence of x's looks like now, it's quite a bit different from before. And I think one of the things that you can see is that before, our x's were persisting a lot longer in states 2 and state 1 when they were transitioning there. But because our transition probabilities are increasing as a function of time, one of the things that is you can see here is that early on in the time series, the persistence probabilities were high, and so the probability of being in state 1 at time t+1, given that you're already there, was higher. And so we see these longer sequences of 1s and 2s versus later in the time series, as those transition probabilities increase, the persistence probabilities have to decrease to compensate. And so we see a lot more oscillation or transitioning from state 1 to state 2. Okay. So that's kind of the nuts and bolts of the transition or the model for the x's, the latent process. Then we think about how to relate our data, our y's, to that process. And so I think those states are discrete, but our observations can be continuous data. They can be certainly other kinds of data that we'll talk about. But we want to make our focus is what is going to be our estimates of gamma, and then also we care about what people who work with HMMs call emission probabilities, which are, if we generate a sequence of states, how likely are states at any particular time step? So what's the probability that X is in state 2 at state 37, or what's the most likely sequence of states for the system? So just to add on the observation error to our simple simulations here, if we kind of go back to where I started with, where we don't have time varying transition probabilities, we can just, again, simulate our initial kind of state vector, our x's, which is our vector of 1s and 2s. But then we need to have our data model down here. And so I think, because we have a 2-state vector, I just wanted to simulate, kind of say, let's pretend our observation model is normally distributed. There's 2 states, kind of a low and a high state, with a mean of 1.2 and 5.4. They have the same variance, and so this is basically our data model down below. And so when we look at what that looks like when we kind of layer this on top of our x's, we get our observation model here. So now all of a sudden it's much harder to see that the latent process where we were transitioning from state 1 to state 2, for example, but it's actually there. Okay, so sticking with our data wise, there's a lot of quantities of interest that people can calculate using HMMs. So one of the most common things is kind of what's the marginal distribution or the probability of our data y sub t. So this is useful for thinking about things like calculating leave one out cross validation, which we'll talk about later, or thinking about the predictive abilities of these different models. If you were to compare a model that included covariates to one that didn't, you would need to do some kind of validation or comparison. And so the way to do this, or one way to do this, is to think about taking your likelihood or the probability of your data y and breaking it in kind of to these two chunks. And so the first chunk just represents, for every time step in the sequence, the probability of being in a state that a certain state is equal to the probability that xt is equal to a certain state. times the probability of the data given that state. So thinking about our x's before, going back from 1 to 2, it was oscillating from 1 to 2. This represents the probability of x. I'm sorry, the probability of our data given that x was in state 1 times the probability that x is in state 1. And so I think this is kind of a little bit into the weeds. We don't need to really worry about it for this class, but just an example of what you can do with it. Again, I think I'll probably skip that slide. And thinking about, in terms of the estimation here, we can do the estimation either in a maximum likelihood framework or in a Bayesian framework. We'll talk about both of these kind of briefly today. This is just some of the background algorithms for the maximum likelihood routines, probably beyond the scope of this, but it's important to understand kind of the two different approaches here. There's what's called the forward-backward algorithm, which is calculating the probability of an observed data sequence. So our observed data sequence is just our, thinking back a couple slides, our sequence of observed data are Y. And there's another algorithm that's also popular called the Viterbi algorithm. And this is useful for generating the most likely sequence of states. And so I think that there's a couple, when I think about examples of the Viterbi algorithm in practice, I think that one of the most common applications is something like spell checking. And so if you're using a spell checker in like Microsoft Word or something, and you have a typo, it tells you what word it thinks that it is the correct answer. That word that pops up is not necessarily, each letter is not treated independently in terms of, it's not calculating the probability of each letter being most correct. It's calculating what's the most likely sequence given all the data, basically all the letters in the sequence. So it's giving you the most likely sequence of states rather than kind of the first approach, which is calculating the probability of each data point independently. Okay, so the forward-backward algorithm, which is kind of what we'll be using in some packages in the next couple slides, are thinking about these forward probabilities and backward probabilities. And so the forward probabilities are just calculating the probability of being in a certain state given your data up to that point. And so it's not looking forward. It's just using what's the probability that it's raining today given that it's rained intermittently for the last 10 days, which is our Y's from 1 to today, basically. Then our backward probabilities are more forward-looking. So the probability that the next probability of the next 10 days being dry, given that it's raining today, is what our X state would be. So that's kind of just the language for thinking about this in terms of when we think about the output. And so I think thinking about some specific applications, I have a couple examples to kind of work through. The first is thinking about this is a time series of rainfall data in Seattle from a couple years ago. This was just accessed, I guess, in 2018, 2019, so about 2 years ago. This is the days since November 1st. And so in this case, this is about a 2-month window. We could model that rainfall data directly, but I think it's a pretty easy, simple application of an HMM. So we just want to model whether or not it's raining on a particular day, which is of course not that interesting because we actually know how much it rained, and so we can quantify that. But we can also turn that into a binary variable. So it's just a categorical rained or not. And this is what that data looked like when we transfer it from the previous slide to just this binary 0 and 1. Okay, so questions we might be interested in with this data are things like, what's the probability that it's going to rain tomorrow given that it's raining today? Or what's the probability of it raining tomorrow given that it's not today? Thinking about persistence, how long on average might we go without experiencing any rain? And so these are, these are all things that you could calculate directly from the data, given that we assume that the data doesn't have any observation error. But just for practice, we'll use an HMM to answer those kinds of questions. Okay, so if you did want to calculate this from basically the raw data, this is how you could do that, just based on creating some difference variables. But we'll be using a different package. So early on, I talked about this DETMIX S4 package. There's a really good vignette they have for fitting these types of models. It's it's fairly fast and flexible. So the DETMIX S4 package has this function called DETMIX, and it takes in a formula that I think everybody's probably familiar with, using a LM formula, fitting a LM or GLM in R. This formula is exactly the same syntax, and so in this case, we are going to set through what each of these different arguments kind of represents. So the first line is just whether or not it rained, and so in this case, in R, the tilde with a 1 just represents the intercept-only model, so we're not including any covariates. We specify the number of states, which is going to be 2. It's going to be rained or not. Again, that's something we specify a priori, and we don't really let the model decide. And then third is the transition, a formula for the transition probabilities. As I kind of alluded to earlier with the example of including a covariate in the transition probabilities, you can include transition probabilities as a function of covariates here, but we'll make this simple and just include an intercept. The family is just like a GLM. We can specify what the response distribution is. In this case, we have a binomial because our data are zeros and ones, but you can include a wide suite of other kinds of variables. You can include certainly continuous variables that are normal or gamma, or beta distributed. You can have Poisson and negative binomial responses, multivariate, multinomial responses. So very flexible. We said that we stepped through this. Covariates, not time varying. There's a lot of families, as I said. And so then when we fit this model, as I was talking about, one of the quantities of interest in an HMM are these gamma, these transition probabilities. So when we fit this model, and all the code for fitting the model was hidden on the slide, but it's just this fit function, and this is kind of what we get as output. So the probability of transitioning from state 1 to state 1 is 77%, and vice versa, it's 59% in state 2. And so state 1 here was not raining, state 2 was raining. And I think it's important to think about these probabilities for a second. And the reason I've got the seed up here is I just wanted to show that these results are fairly sensitive to what we choose for the seed, unfortunately. And so in this case, I picked a random seed, fit the model. I'm going to pick another seed, 1, 2, 1. And so basically what happened is you can see these switched. And so if I go back and forth, they switch, but they kind of switch in a funny way, in that they just got reversed, right? So before it picked state 1, had a 77% probability of persistence, but what it called state 1 in this first iteration, it's calling state 2 in the second iteration. And so this is just kind of a weird thing to know about HMMs, is that you can't necessarily specify the label of whether whether state 1 corresponds to rain or whether state 1 corresponds to no rain. And so it's something that you have to kind of determine from output, but these results can be sensitive with how basically how we initialize the model affects what our estimates are. So there's a couple, and sometimes even worse, even more sinister, our seeds can affect these estimates by just a small amount. And so changing the seed will change these estimated probabilities in a way that, maybe instead of 0.59, maybe 0.57 would be the estimate for a certain seed. And so to really convince ourselves that we got the most likely solution, sometimes we have to do this a large number of times, or you basically run the HMM a large number of times. So one way to do that is to just kind of do another kind of brute force approach, where we would maybe use AIC to find the best model. And in this case, what we would do is run this loop a large number of times, maybe 100 times. We're going to keep refitting the model 100 times from 100 different starting locations. And then after each fit, we can just check if the AIC of our fitted model is better than the best that's ever been observed. And if it is, we'll keep it. And if not, we'll just move on to the next one. So especially in some of the applications that I've been working on, where we have a large number of states, say 4 to 5 states, and hundreds or thousands of data points, it's fairly easy for the likelihood to be to kind of trick us, because it's relatively flat in places and hard to maximize. And so in this case, we often have to run this hundreds or thousands of times to really verify that we're in the best spot. Okay. Okay, so moving on to a slightly more complex example. So I pulled some data together from some of the Cal Coffee cruises in Southern California, and these have been used to kind of, specifically I pulled some species that have been used to kind of indicate cool versus warm ocean regimes. There's a species of California smooth tongue that is going to be used here. And so this is a really complicated survey. It's spatially gridded. If you were to do this for real, just as a caveat, you would want to use either spatial models or more complex approaches than what I'm doing here to estimate abundance. But essentially what we did was took the mean catch per unit effort over the entire survey area over the spring period. And that's what this mean catch per unit effort here represents. So these are now annual estimates of catch per unit effort. And we can set up a hidden Markov model to fit these data. As if I go back to the last slide, so these data are they are positive, and they're skewed. They have a long tail because they're catch per unit effort. And so I think it's often the case that we would log transform these. So that's what we're doing here. We're just going to log transform abundance, fit a hidden Markov model to 2 states to try to diagnose that cool versus warm regime. So in this case, again, we have an intercept only model. We have 2 states, so fairly simple, and then we can fit our model. All right. So there's a couple things we can do with this output. The first is looking at predictions from our fitted object in DETMIX, and we can start with those state probabilities, which are not the same as the most probable state trajectory. So these X's represent the most probable state at each time step, if that makes sense. So in this case, this is, I'm sorry, this is the this is the Viterbi sequence. So it's the most probable state that we're looking at, which is right. Yeah, that makes sense. Okay. So it's the most probable state sequence, which represents the transition from cool versus warm. We see that when it's in state 2, abundance is high, and when it's in state 1, abundance is low. So it's kind of the opposite because of that labeling issue from what we might expect those states to be labeled as. So unfortunately, like some of the other ARIMA type models that we've talked about in this class, DETMIX doesn't have a predict or a forecast function, but we can let's see here, Mark is here. We can do that or get the means out of these different states with just kind of the summary function. So this is kind of what our state, these are kind of the underlying states, as well as the means from that fitted object. So this would give us kind of a rough estimate of what the mean log abundance was in cool versus warm regimes. Okay, so if we think back to the last slide, this fits okay. But if you remember from any of the slides about autocorrelation, et cetera, from week 1 and 2, if you think about this kind of what autocorrelation would look like over a time period like the last decade, this would look atrocious because these residuals are autocorrelated. The model clearly isn't fitting awesome here. And so I think there's probably more complicated ways to fit this. You might think, well, sure, maybe there's been kind of a warm blob in the last decade. There's been maybe some regime change in 2015. Maybe the last 3 or 4 years have represented kind of a new state of the system. So maybe instead of fitting this 2-state hidden Markov model, we should just fit one with 3 states instead to really capture things that are going on in recent years. So when we do that, this is super simple. You can just do the exact same model, change the number of states to 3. What's interesting is when we fit this model, we get actually a worse AIC value. So the AIC for the 2-state model was about 119. It's about 122 for the 3-state model. So we get a worse fit when we do that 3-state approach. Okay, so we found some more support for the 2-state HMM, but what I've often found in practice is that the opposite's true. So especially for some of these models with 4 or 5 states, if you start adding states to a hidden Markov model and doing this kind of model selection using AIC will often tend to support models with more states. So if you have a model with 5 states and you try that 6th state, it often will have better AIC support, or 7 states even better. So it gets frustrating because you don't often get data support from AIC. And so I think there's a few ways that we've dealt with that. The first is just kind of using Occam's razor. So just talking to the biologists about if you're modeling behavioral states, how many states are we actually able to infer changes about? How many do we actually care about? So in that case, sometimes simpler is better. There's also been quite a few papers, including this really good one, with a focus on animal movement, but thinking about how to select the most parsimonious number of states in these kinds of models. So I think this is kind of an area of ongoing research, but it's just something to be aware of if you apply these types of approaches. And you see that as you start adding states, you get better and better fits, and pretty soon you're fitting the data perfectly, but you have 37 states in your model. So it's can be a challenge. Okay, so these have been largely kind of univariate HMMs, but I think it's often the case that these are actually more interesting and useful when they're applied to multivariate time series data. So in the cases that we've talked about so far, like with cow coffee data, we just had a single species abundance through time. In this case, though, what we're going to do is start adding more time series, and we're going to assume that the state process, so the X's, the cool versus warm regime for the cow coffee example, for example, are going to be exactly the same. But where they might differ, where the 2 types of time series might differ are in their lengths. So we might have patchy data for one time series and not patchy data for another. And then they can also differ with their error distributions too. So HMMs are super flexible in that you can include, maybe you have 3 time series of binomial observations, presence absence, with maybe a Poisson response for a 4th time series, and maybe a normally distributed time series as the 5th. And they can all be included in the same HMM as long as the assumption that all of those represent different observations of the same latent state is met. So, so super flexible. If we want to apply these as a two-state example, we can extend the Cal-Coffee example before to just include a second species. So in this case, it's one that tends to be pretty correlated with our initial smooth tongue example. And so, not getting into the data too much, we're just going to create a data frame with that second species where we have observations in each year. And again, we're just going to log transform abundance. In the big switch here in the det mix arguments are now, instead of passing in a single formula, we pass in a list of formulas. And so in this case, each of the different species has an intercept. And then we also have to pass in our family argument now as a list. And so this just tells the algorithm whether we're going to, how to specify the families of each of these. These are both Gaussian, obviously, so we don't have to do anything fancy. But if you did want to specify, binomial or Poisson or other kinds of data, you could do that here. Okay, so this is, so it's also useful for if we have time series of different length. So if we started our survey of the second species, halfway through the time series and we're missing the first half of values, we could do that. There's a useful argument that I haven't talked about called n times, which is useful for looking at basically the length of each of those time series. We don't have to do those here, but yeah, just to summarize kind of what those represent. So the HMMs are super useful at identifying kind of our latent state vectors, our X's, and estimating those gammas or those transition probabilities between different states. The estimation of HMMs in R is generally done with maximum likelihood methods. These approaches are super fast, even for models with 4 or 5 states and thousands of data points. It generally takes a couple minutes to run. They're very fast, but as I was mentioning, there's this label switching problem where states can get mislabeled, and you have to really dig into what they actually mean in the output. And then the different approaches can also get stuck. So I think, as I said, the likelihoods can be pretty flat and hard to maximize. And so you often have to fit these models, hundreds or more times to make sure you really get the best solution. And then I think the last thing that I'll just acknowledge and make a note of is that for folks who are going to be interested in applying these methods for the class, in my own work especially, I've done this more in a Bayesian setting. And so I think there's a couple different software packages out there for estimating HMMs in a Bayesian framework. I think that the most popular are probably using tools like JAGs or bugs. And so I've included at the end of this lecture, there's about 10 slides or so that kind of walk through some different examples of how to build a model in JAGs and how to fit that. And then there's also, so Nimble is kind of the latest iteration of the bugs in JAGs world. And that is also very flexible for fitting these types of models. I think the Bayesian models are really interesting because it becomes much easier to do things like, instead of just modeling an HMM that's autoregressive that's a first order process, you can make it a second order process. So instead of being just dependent on instead of having the process just be dependent on the previous time step, it can be dependent upon the previous 2 time steps. And so I think once you start thinking about those processes or complexities, I think that going with the Bayesian code is probably a better and more flexible approach. Stan is also out there as a tool. There are some simple HMMs out there in Stan. In general, though, I think that those can be pretty complicated because the samplers in Stan are not designed really to be categorical variables. They're continuous, and so I think there's kind of ways to trick Stan to estimate Cormac, Jolly, Sieber, and those types of marker capture models. But But for simplicity in this class, I think that JAGs and bugs are probably a much easier approach. So